Your lecturer is Dr. Ron B. Davis, Jr. Dr. Davis is a visiting assistant professor of chemistry at Georgetown University, where he has been teaching introductory organic chemistry laboratory since 2008. He earned his PhD in chemistry from the Pennsylvania State University. Dr. Davis's research has been published in such scholarly journals as Proteins and Biochemistry, and has been presented at the annual symposium of the Protein Society. He also maintains an educational YouTube channel and provides interviews and content to various media outlets, including the Discovery Channel. At Penn State, Dr. Davis received a DeLillian Fellowship and the Danwa Teaching Award.
Most of our understanding of the chemistry of carbon-based compounds has been accumulated since the discovery of some of the most fundamental elements less than 300 years ago. In fact, it was only about 3,000 years ago that ancient Greek and Chinese thinkers were the first to postulate the existence of fundamental substances at all. But Mother Nature got a head start on us about 3 billion years ago, when the first living organic chemist on Earth came into existence. Here's one: cyanobacteria, believed by most to be the first living organisms to inhabit the face of the Earth. Fossil evidence shows that these bacteria took up residence here about 2.7 billion years ago. Now, these little creatures fed, grew, and self-replicated. They contain lipids, proteins, and nucleic acids, all the usual suspects from a modern biochemistry course. And for the basis of their biochemistry, the central element upon which they built the molecular machinery which sustained their own existence, they chose carbon. Through the process of evolution, the foundations of their biochemistry were passed on to each and every living thing that has ever lived on Earth. As unicellular organisms continued to evolve and their chemical systems grew in complexity, more ordered eukaryotic cells formed with organelles to carry out specialized functions. Then came multicellular aquatic organisms and terrestrial plant life and animals. But through 2.7 billion years of evolution, to the best of our knowledge, life as we know it has never, not once, abandoned its choice of carbon as the foundation onto which it builds its most essential chemistry. With almost 100 naturally occurring elements and such an expansive time frame, you might think that somewhere, sometime, under some set of environmental stresses, life would try a different element and have some success. Yet all evidence points to the contrary. It simply hasn't. But why? Carbon is not the most abundant element on Earth, nor is it particularly scarce. It's easily made in the furnace of a star like our Sun, but then so are the other 25 of the lightest 26 elements in our universe. At the 6th smallest in size, its atoms don't have an unusually complex or simple structure to them. It can't stack up to the ferocious reactivity of elements like fluorine, nor is it rock stable like helium. At a glance, it seems that there is nothing special about carbon. But in a way, that is just what makes carbon such a perfect choice to serve as the scaffold for the chemistry of life. It strikes the right balance of properties which make it uniquely suited to its role in living systems. And it's this balance that makes carbon the undisputed centerpiece of living systems. But carbon's story doesn't end there. Not only is it central to the chemistry of life, but it also serves as a structural basis for materials of incredible strength, fuels with tremendous amounts of stored chemical energy, and life-saving medicines. Carbon's story is nothing short of incredible. So incredible that we've honored it with something no other element has, its own branch of chemistry. And we call this branch organic chemistry. Today, I would like to discuss the essentials of organic chemistry. We'll be looking at what organic chemistry is, how organic chemistry is practiced, and where we can find organic chemistry operating in our world. And don't fall into the trap of thinking about the science that goes on in laboratories. Organic chemistry is going on in places many of us may not typically imagine. We can find it at work all around us in places as distant and exotic as deep within the Earth's crust or interstellar space. It's also all around us, going on right now inside countless manufacturing facilities around the world. It's powering the engines of the vehicles passing by this studio, and it's even going on in your own body right now. During our time together today, I'll be discussing what is arguably one of humanity's greatest intellectual achievements, the science of chemistry. Then, we'll explore how our growing understanding of how to manipulate the molecules of life eventually led us to establish the discipline of organic chemistry. Next, we will briefly discuss the structure of the fundamental unit of all known elements, the atom. We'll also take a look at a portion of the well-known tool of chemists, the periodic table of the elements, which helps us to predict their behavior and their properties. Here we will be answering the question, what is it about carbon that makes it nature's choice to serve as the basic scaffold for many of the molecules we depend on to sustain and improve life? Finally, we'll take a look at a few real-world examples of how carbon atoms come together to form the backbones of the molecules that become our building materials, food, fuels, drugs, and so much more. By the end of our discussion, I hope that you'll have a deeper appreciation of organic chemistry, of its definition, its origins, and how it helps to improve the quality of life of nearly every human on the planet. If I'm able to succeed in that endeavor, I invite you to stay for the next 35 lectures to learn even more about this well-understood but ever-evolving and growing branch of chemistry. So first, let's define the science of chemistry. Scientists define chemistry as the study of matter and its properties, particularly those of atomic and molecular systems. One of the defining tenets of chemistry is the idea that all substances can be broken down into their basic elements, which can no longer be subdivided while still retaining their identity. Ancient Greek and Chinese civilizations are often credited with first theorizing the existence of fundamental elements that combine to form all other substances. Both of these civilizations postulated that air, water, earth, and fire were among these elements. Of course, today we know this list to be inaccurate. Now, the realization of this began in the 18th century, when a French chemist and nobleman named Antoine Lavoisier became the first to catalog the existence and properties of some of the elements as we know them today. Lavoisier started to develop this catalog when he challenged the 2-millennium-old notion that water is an element. He knew that if water were an element, then he should not be able to decompose it into simpler substances. But he noted that heating water in the presence of iron in a closed system had two intriguing effects. First, it turned the iron to rust, which appeared to increase the mass of the iron sample. And second, it produced a vapor, which could be collected separately and then burned in air to regenerate water. What was going on here was that the iron was acting as a sink for oxygen, pulling the oxygen out of the water to become iron oxide and leaving hydrogen gas behind as a byproduct. Any doubt that water had in fact been decomposed was eradicated when Lavoisier showed that he could burn the collected gas to reform his water. So Lavoisier had successfully disassembled and then reassembled water in the 1700s. Lavoisier's tinkering proves that, contrary to ancient thought, water is not an element, but instead is made up of more basic materials in combination with each other. But Lavoisier's best efforts to decompose the resulting gases from his first experiment failed, prompting him to categorize those as elements. Now, since it could be burned in air, at least the gas that he collected, could be burned in air to produce water, he dubbed it hydrogen, meaning water maker. Lavoisier's classification techniques quickly gained favor in the scientific community, and the list of identified elements rapidly grew in the decades following his work. In the late 1800s, a Russian chemist by the name of Dmitry Mendeleev took notice of something extraordinary. Mendeleev realized that when he listed the known elements in order of increasing atomic mass, they formed a series of materials, some of which seemed to have similar sets of chemical and physical properties. And when he spaced these elements so that similar properties repeated every 8 positions in the list, he could account for all the known elements of his day. But what is even more amazing is that the gaps left in Mendeleev's table allowed him to predict the properties of yet undiscovered elements, all of which eventually turned up. So Mendeleev's true genius was to visually demonstrate this repeating pattern by wrapping the lines of atoms into rows, much like lines of text in a paragraph. And by doing this, he created a table with columns of elements sharing similar chemical properties. We call these columns from his table groups of elements. More than 200 years later, his pivotal invention has been refined and expanded into what we know as the modern periodic table. So we've seen that chemistry is the study of matter and its properties. Given that all objects in the universe can be classified as matter, and that nearly all of this matter is made up of atoms and molecules, you can understand why chemistry is an extremely broad field of study. And with such a tremendous field to cover, it's easy to see why those practicing the science divide their interest into subdisciplines, like biological chemistry, physical chemistry, organic chemistry, and more. And while each subdiscipline is a topic worthy of study and appreciation, for the duration of this course, we will be interested in organic chemistry. Although there will inevitably be times when organic chemistry bleeds into these other realms. So, what is organic chemistry? When most people think of the word organic, they may think of expensive salad greens, health food stores, or sustainable farming techniques. But to the chemist, the word organic means something very different. Organic chemistry is most simply defined as the study of carbon-based molecules. Compounds such as the hydrocarbons in gasoline, the sugars in the foods we eat, many modern materials, ranging from explosives to plastics, are all built on carbon-based backbones and therefore all fall into this category. The term organic, as it pertains to the study of chemistry, was coined in the late 1700s. It's a reflection of a common paradigm of that day, that only organisms could create these kinds of carbon-based molecules. See, scientists of that day had already successfully isolated carbon-based compounds like urea from biological sources, and it was commonly presumed that living things possessed a special trait known as vitality that was necessary to produce the chemicals of living systems. This dogma persisted for many decades, until 1828, when German chemist Friedrich Wöhler produced urea without the aid of a living organism. Wöhler simply heated the inorganic materials ammonia and cyanic acid in an attempt to synthesize another inorganic material called ammonium cyanate. But much to his surprise, the product of his synthesis was instead urea. Since then, Wöhler's synthesis has become the stuff of chemistry lore. Many chemists point to it as a seminal moment in chemistry when vitalism was disproven and scientists began to realize organic compounds could be made and manipulated not just in living things, but in a beaker as well. In the nearly 2 centuries since Wöhler's inspirational, albeit accidental, synthesis, organic chemists have classified and created millions of organic compounds that enhance the quality of life of nearly everyone on Earth. With over 100 elements in the modern periodic table, we're forced to ask the question, what makes carbon so special? Why does carbon get its own branch of chemistry? Now, the answer to this question lies in a balance of 3 key factors: abundance, complexity, and stability. When we compare carbon to the other elements in the first 3 rows of the periodic table, we'll see that only carbon is able to blend these 3 factors in a unique way. Let's start by comparing abundance. If we were to make a table of the estimated relative abundance of elements in our solar system by mass, we'd see something like this. Many of the elements are so vanishingly rare that they don't even register on our chart. Hydrogen is the clear winner at about 73 mass percent, followed by helium comprising 24%, and then oxygen at about 1%. So out of more than 100 known elements, just this trio makes up 98% of all the matter in our solar system. But coming in at number 4 is carbon, making up somewhere around 0.5% of all the matter in the solar system. Now, based on this information alone, you might expect to find subdisciplines of chemistry focusing on the chemistry of hydrogen, helium, or oxygen as well. Yet these subdisciplines do not exist. These numbers are a bit different when we consider just the Earth, or even portions of it. Now, the truth is we're not quite sure just how much of each element makes up the overall mass of our planet. We do know, however, that as the planet cooled more than 4 billion years ago, much of the denser elements like iron and nickel found their way to the core of the planet. Intermediate-sized elements like silicon and aluminum were sorted into the crust, leaving behind even lighter elements like carbon in higher concentrations at and near the surface. So carbon is ever present near the surface of the Earth in environments which might support life as we know it. But our best estimates of the amount of carbon in those environments, the world's atmosphere, oceans, and crust, is never more than about 1% of the total mass. This means that there's enough carbon there to work with, but if abundance were the only concern, then there would clearly be better choices. And yet, when we turn our attention to our own bodies, we see that we are actually made up of about 20% carbon by mass. This is far more than the relative abundance of carbon in our environment, far more than the oceans, the atmosphere, or dry land. So carbon is available, but so are many other candidates. So what's going on here? What makes the difference? Why use carbon? Well, clearly there's something about carbon that makes it a better choice for the structural basis of organic molecules. With such an enormous amount of carbon in biological systems, relative to the environment around us, it's easy to see how the concept of vitalism was originally conceived. But if vitalism has been shown to be an invalid theory, why is it that carbon has been selected by nature to be the backbone for the molecules essential to life? Why would life go to the trouble of increasing carbon content 20-fold over what was available in the environment, especially when there are much more abundant elements available, like nitrogen, which makes up 78% of our atmosphere, or oxygen and hydrogen, which combine to make up a staggering 96% of the mass of our oceans, or silicon, which comes in at a very respectable 27% of the Earth's crust? In order to answer this question, we'll have to take a look at the bonding behavior of carbon compared to other, even more abundant elements, and try to explain a bit better why carbon is so special when compared to them. But before we can have this discussion, we first need to consider the structure of atoms. All atoms consist of a positively charged nucleus, surrounded by a cloud of negatively charged electrons. The electron clouds of 2 or more atoms can interact with one another in ways which confine those atoms to a fixed distance in space. We call this interaction between atoms a covalent chemical bond. Now, one of the remarkable things about Mendeleev's brainchild, the periodic table of the elements, is that it actually predicts the maximum number of these covalent bonding interactions that a particular atom can form with others. If we start from the leftmost column of the table, elements of the first group can form 1 bond at most. Those of the second can form 2. And the trend continues until we reach the 4th group. After this, the maximum number of possible bonds begins to decrease again to 3, 2, 1, and finally 0. This makes hydrogen a relatively uninteresting nucleus from the bonding perspective, since it can only form a single bond with another atom. So hydrogen atoms are the end link in chains of bonded atoms. They can't bond any more atoms to continue creating a complex structure, because doing so would require that they make a second bond. That makes hydrogen the placeholder of organic chemistry, occupying locations on a molecule in which differing groups of atoms might be placed to alter that molecule's identity and reactivity. Helium, nature's second most abundant element overall, though vanishingly rare on Earth, appears in group 8 of the periodic table, making it unlikely to form any bonds at all. Helium actually exists only naturally as isolated atoms that don't commonly react with other elements. It's not essential to life at all. In fact, helium's lack of reactivity kept its existence concealed from chemists for nearly a century after the discovery of elements like hydrogen. French astronomer Pierre Janssen first observed helium when studying a solar eclipse in 1868, a century after Lavoisier's work. And it was only after several more decades of searching that helium was finally found to be present on Earth. An English physicist, Sir William Ramsay, found it, trapped inside of radioactively decomposing minerals, not exactly a biologically relevant environment. And our final contender with carbon for the role of backbone molecule is oxygen. Oxygen typically makes 2 bonds to other atoms. In doing so, oxygen can act either as a bridge, bonding 2 different atoms together, perpetuating a chain, or as a terminal atom, making what is known as a double bond. But once oxygen's 2 bonds are established, it is satisfied, and there are no additional locations available to decorate or modify an oxygen chain. Using an oxygen chain as a backbone would then lead to a rather dull set of molecules, just a set of ever-lengthening chains of oxygen atoms with no additional complexity at all. But carbon interests organic chemists because it's found in group 4 of the periodic table. This means that it can, and often does, form 4 bonds to complete its electron shell octet. This is more bonds than any other element in the second row of the periodic table. And this allows carbon to bond to itself to form not only chains, but branched structures, loops, and many, many more. Furthermore, these complex carbon scaffolds often have remaining unsatisfied bonds, which can be terminated by hydrogen atoms, or decorated by bonding them to any number of other candidates as well. So it should be clear now that those extra bonds that carbon can form are going to make all the difference. But we aren't quite done yet. If you're keeping score, we still have nitrogen and silicon on the list of possible backbone elements for larger complex scaffolds. Nitrogen and silicon have withstood the test of both abundance and of bonding complexity, with nitrogen abundant in the atmosphere, able to form 3 bonds, while silicon makes up a large part of the Earth's crust and is able to make 4 bonds. So we're close. But what separates carbon from nitrogen and silicon is the last factor that we have to consider: strength. Now, you wouldn't build a skyscraper with a frame made of cardboard, would you? Now, of course you wouldn't, because the structural support has to be stronger than the doors, windows, and walls which it holds in place. Organic molecules are no different. Just like a building, they need a support structure tough enough to hold the functional parts of the compound in place. Now, any candidate for this role will have to be tough enough to withstand the conditions which cause other parts of the compound to break their bonds and react. So, the final factor leading to nature's choice of carbon for small molecule scaffolds is the stability of the carbon-carbon bond. You see, bonding is an energetically beneficial arrangement, and a bond's strength is usually measured by the amount of energy required to separate the bonded atoms. Scientists call this the bond enthalpy. So, the larger the bond enthalpy, the harder it is to pull 2 bonded atoms apart, and the stronger the chemical bond is. If we compare the experimentally determined bond enthalpies of all first, second, and third row elements in the periodic table to other atoms of the same kind of element, we can see that only hydrogen and boron form single bonds to other atoms of the same kind with similar strengths to carbon. So hydrogen does bond to itself strongly and is very abundant, but its 1 bond limit rules it out. Boron can form stable bonds with itself in networks with up to 3 bonds, but it's so vanishingly rare in the environment that it simply can't play an important role in the chemistry of life. Our last 2 viable candidates, nitrogen and silicon, are finally ruled out when we consider bond strength. With bonds only about half as strong as carbon, nitrogen can't compete. And even silicon, a favorite candidate of sci-fi aficionados everywhere, as carbon's alternate, because of its abundance and ability to form 4 bonds, fails to meet the final standard, because a covalent network of silicon atoms would simply not be stable enough to survive chemical reactions meant to modify other bonds within the molecules it would comprise. So, if we consider the first 3 rows of the periodic table, removing elements of prohibitively low abundance, elements incapable of forming more than 2 bonds, and those which do not form strong single bonds to themselves, it now becomes obvious how these 3 factors make carbon uniquely suited to the formation of molecular scaffolds. So I hope that by now I've convinced you that carbon is nature's best available choice for the construction of molecular scaffolds because of its abundance, complex bonding, and the stable bonds it forms with other carbon atoms. Now I would like to show you specifically how carbon atoms can combine to form distinct structures and how decorating these structures with other atoms can lead to a rich and diverse library of compounds. Part of what makes carbon scaffolds so prolific and diverse is the multiple ways in which the 4 bonds to carbon atoms can arrange themselves in space. Remember that chemical bonds are formed when electron clouds overlap, and this produces a region of dense negative charge between the atom's nuclei. So these bonds made up of negatively charged electrons can be thought of as being negatively charged themselves, and just as you might expect, because they're made up of like-charged particles, they repel one another, positioning themselves as far apart as possible around the central atom. So when a carbon atom is connected to 2 other atoms, either by 2 double bonds or by a single bond and a triple bond, the connected atoms are 180 degrees apart from one another, forming a linear geometry among those 3 atoms. When a carbon atom is connected to 3 other atoms, 2 atoms by a single bond and 1 other atom by a double bond, the atoms form a planar geometry in the shape of an equilateral triangle, with bond angles of 120 degrees among all of the atoms. We call this type of geometry trigonal planar. But the real magic happens when we use all 4 bonds to connect to 4 distinct bonding partners. In this case, a planar geometry would require 90-degree bond angles. But giving these bonds access to the 3rd dimension allows them to separate even more from one another, forming bond angles of 109.5 degrees. And we call this arrangement tetrahedral, because tracing lines among all bonded atoms produces the shape of a tetrahedron. So, by bonding carbon atoms together using some or all of these geometries, linear, trigonal planar, and particularly tetrahedral, we can form almost any 3-dimensional arrangement imaginable. But notice that in all of the examples of carbon scaffolds shown here, there are remaining bonds terminated by hydrogen atoms, which could easily be replaced by other sets of atoms. This means that each carbon scaffold can act as a backbone supporting hundreds, thousands, or even millions of distinct atom combinations. By designing molecules in this way, chemists are able to create compounds with very specific and rationally designed shapes, physical properties, and reactivities. As you can probably imagine, this quickly leads to a virtually limitless library of possible compounds, all of which rely on the stability and geometry of their carbon scaffold to function. As we progress through the course, we will take a detailed look at how building upon these scaffolds leads to libraries of compounds with extremely diverse properties. And I'd like to close our conversation today with a few examples. Consider compounds with only 6 carbons in their scaffold. Now, using these 6 atoms, we can construct a variety of scaffolds, such as straight chains, branched scaffolds, cyclic scaffolds, fused bicyclics, and even more. Now let's see what we can do with just 6 carbon atoms in a scaffold and a little bit of imagination. Let's bring up those 6 carbon atoms and place them in a linear chain. If I saturate this structure with hydrogens, meaning I put hydrogens at all the remaining bonding locations on the carbons. I create a molecule known as hexane. Hexane is a component of motor fuels. But if I make just a few alterations, inserting some oxygen atoms, I create a molecule known as glucose, a simple sugar found in foods and used by your body to store energy. If we make a few more changes and throw in a nitrogen atom here, we create lysine, an essential amino acid which your body uses to make enzymes in tissues. But let's go back to our carbons and rearrange them. Let's create a branched chain now. This branched chain, when saturated with hydrogens, is isohexane, yet another component that's blended into motor fuels. If I add a little bit to it, I can create leucine, yet another amino acid essential to life. But I can make another change and create isohexyl acetate, a flavor and fragrance additive that smells a bit like fruit. Let's continue. Let's take those carbons and put them into a ring. When I saturate my six-membered ring, I create cyclohexane, yet another motor fuel. But that's not all cyclohexane can do. If I make a little change, I can create the heart medication, cyclohexyl nitrite. Or I can make the artificial sweetener cyclamate. One last example. Let's take those atoms again and put them into a ring, but this time, let's put them into a ring where they have a different bonding structure to one another. This is called a benzene ring, and when it's saturated with hydrogens, we call that molecule benzene, an industrial solvent, and also one that we use in the laboratory quite frequently. But just a small change to that structure gives me aspirin, popular analgesic. Yet another change gives me TNT, a high explosive. Impressive versatility and variability, isn't it? All done with just 6 atoms. So all of these possibilities and countless more are accessible with just 6 carbon atoms. Not only can the number of carbon atoms in scaffolds be changed, but there is a long library of reactive groups made from other elements that can be bonded to these carbon scaffolds that we've discussed today. In tandem, these two factors combine to form a practically inexhaustible library of possibilities. So let's review what we've discussed today. We've explored what organic chemistry is, how it got started, and how our understanding of it has changed over the years. We've also scratched the surface of explaining how carbon's abundance, bonding complexity, and bonding strength all combine to make it such a unique and versatile element for building complex small molecules. Finally, we've looked at how the decoration of these scaffolds with groups of other atoms can lead to a diverse library of useful compounds. Next time, we'll take a much more detailed look at atomic structure and chemical bonding, examining exactly why some of the trends predicted by the periodic table exist. And in doing so, we will continue to deepen our understanding of the complex geometries of the carbon frameworks on which every living thing relies. I look forward to seeing you then.